not certain that people will do it. So I've prepared some simpler things, some things which are based on what you already know. Okay, so let me. So something on the chemical side, something on the what we have already done on the bio portion. So you please do it, and tomorrow if there is some questions, I can answer you. So let me give you those very simple slides. So what were we left with in the chemical part? And what were we left with in the bio portion? In the bio portion, we were left with adding product, extracellular product, which is different from biomass. So that's something that we should be able to do. Okay, then we are left, and we were left with available electron balance, and that's a little bit more important thing, which is a new aspect as to how that conservation takes place from substrate and how those electrons are transferred to oxygen, to product, to biomass, right? So that I can cover tomorrow, and we should be able to do a proper job on it. So this product stoichiometry part, I can give you a assignment type of thing, and you can ask me how to do it. We should be able to do it. Second thing, on the chemical thing, see, we have to do chemical reactions. Now that, as you know, in all heat changes, energy balances, there are two types of effects: a sensible heat change and then a heat of reaction. Now, sensible heat changes you have actually already done several times in physics and chemistry. You know, you have done these calorimetric experiments and so on. So now for a chemical reaction, what happens is that you have all the various species. Okay, all the various species, and all the various species will have their own specific heats, right? Now, if the specific heats are given as functions of temperature and pressure, we can always integrate them, and then we can find the sensible heat change. It's just that the data on specific heats as a function of pressure is not readily available. Okay, now, however, as you know, all real gases, when they are extrapolated to low pressures, to zero pressures, behave like an ideal gas, right? So it turns out that this pressure dependence, even for real systems, the pressure dependence of Cp or Cv or of specific heats is a very weak function of pressure. However, they are very strong functions of temperature. So even for real systems, real gases, etc., which is called ideal gas state, not ideal gas. So what we are doing is we are neglecting the dependence of the sensible heat change or of Cp as a function of pressure. And we are saying it's only strongly, primarily function of temperature. And then we can integrate Cp dt if we know Cp as a function of temperature, and we can get the sensible heat change, right? So that is one thing we need to do. The third thing is that is sensible heat changes are easy. All you have to do is just integrate. And as I told you, we just neglect the dependence on pressure. This doesn't mean the system is ideal. It just means that compared to the dependence on temperature over a wide range, the dependence on, even if you could incorporate the pressure differences, they would hardly give you 5 to 10% error at low pressures. Up to 20 atmospheres, it will hardly change anything. So that's something we have to do. Only thing is, you know, to integrate. Now, generally, when you have functions of temperature to integrate, I mean, it's generally given Cp as a function is alpha plus beta T plus gamma T squared plus delta T cubed, or sometimes alpha by T plus beta by T squared. So it's just a cumbersome integration. It's not difficult. It's just that a little time consuming. So the question that I'm interested in is there a simpler way to do this integration? So that's something that we have to spend at least half a class on. And there is, okay, and then there is data available also. So, you know, in a 1 hour exam or so, you don't want to spend a long time just integrating things. So that's something we need to worry about. Now, as you know, you have done the basic thermodynamics from school, if it's a closed system, okay, and work changes are very small, then Q is equal to delta U. If it is a flow process, that steady state flow process, like we did in the first part of our course, then Q is equal to not delta U but delta H. Okay, Q is equal to delta H because the PV part gets added. So now if we can figure out the delta H changes, we can say that is the heat effect, right? And as you know, if Cp is given, either the pressure is constant and you can integrate and find delta H because delta H is integral Cp dt, right? Or even if pressure is not constant, and as I said, we can make the approximation that the variation of Cp with pressure is very small compared to the variation with temperature, and then integral Cp dt will also give you the delta H heat effect, and that we can equate to Q, provided all the other potential energy changes, kinetic energy changes, shaft work in a steady state process is small, and that's generally a very good approximation. I mean, we don't need to worry about it. Okay, so that is how we need to deal with in this week, the coming week, the sensible heat changes. But then the other thing is chemical reaction. Chemical reactions also have the heat of reaction, right? Every chemical reaction, as you know, has a heat of reaction. So we need to also and this heat of reaction is not negligible, okay, compared to the sensible heat change. So we need to incorporate this also in the energy balance, right? So how do we do that? That's something else that we need to worry. So there are many ways, so, and we don't have time to do everything. But one very general way which you are familiar with is heats to calculate heats of reaction from heats of formation of the of every compound, and then taking the stoichiometric of the reaction, and A times the heat of reaction of the reactant product minus that of the reactant gives you the heat of reaction of the reaction, chemical reaction itself, delta HR at naught, at standard state, that is 25 degrees Celsius and 1 atmospheric pressure, 298 Kelvin, right? So heats of formation, the information is readily available. It's there in every thermodynamic table. Okay, I mean, for CO2, NH3, water as vapor, water as liquid, you all know what its heat of formation is. So just by algebraically playing with the heats of formation, multiplying by the stoichiometric coefficient, you can find the heat of reaction. But the problem only is this: the heat of reaction is always at 298 Kelvin. See, pressure, we say we don't care. It could be 1 atmosphere, but even if 10 atmosphere, we say it doesn't change. Hardly changes that because we are neglecting the pressure dependence, right? But our problem is we can't neglect the temperature dependence, and the reaction, whatever reaction you are doing, maybe it's not necessary you're going to do it at 298 Kelvin. You could be doing it at a very elevated temperature, right? 400 degrees Celsius, 500 degrees Celsius, what have you. In a combustion reaction, even higher. In a flue gas system, I mean, 1000 degrees Celsius is also possible. So now the problem is, how do we extrapolate the heat of reaction that is available only at one temperature, because standard heat of formation data is at a standard condition of 298 Kelvin. So heat of reaction also we can only find at 298 Kelvin. So how do we actually extrapolate this and find sensible heat changes and heat of reaction? How do we incorporate all of this when the reactions are taking place at a different temperature other than 25 degrees Celsius? We have to solve that problem. And essentially, Hess's law, and we have to construct an appropriate path, okay, because it's a path function. It's not a path function, but a state function. And if we have to construct another path which gives us the same enthalpy change as for the reaction, but nonetheless we should be able to use the information at 25 degrees Celsius. So that is something we have to do in the next couple classes. Okay, and it's very easy to extend this to multiple reactions because sensible heat changes, you have done the material balance, so you know how much reacts by reaction 1, how much reacts by reaction 2. So sensible heat changes is just integral Cp dt. Absolutely no problem. But now if you have the heat of reaction at, of course, at 298 Kelvin, you have it, if you know what fraction reacts by reaction 1 and what fraction of the substrate of the reactants react by reaction 2, then the weighted mean of that is the net delta H reaction, right? So if half of it reacts by reaction 1, half of it by reaction 2, then 0.5 into the heat of reaction of 1 plus 0.5 into heat of reaction of 2 is the net heat of reaction at standard conditions of 1 atmosphere and 298 Kelvin. Okay, so it's just a trivial thing to extrapolate this, extend this to many reactions, no problem, as long as you have the mass balance. You must know how much of the methane got combusted, let us say, by first reaction, second reaction, third reaction, etc., which is a mass balance problem. So that we have done, right? So our problems are two. One is sensible heat changes. If we don't want to integrate every time, is there a shortcut? Number two, heat of reaction we have to incorporate, and heat of reaction is only at 298 Kelvin. How do we use this when the temperature at which we are carrying out the reaction is different from 298 Kelvin, right? And then on the bio portion, we have to first incorporate product stoichiometry, which is something we have not done. We should have done by now, but we didn't do it last time. That's something we need to worry about today. And then available electron balance is another thing we have to do. We need a full class for that, and ideally I need everybody present for it because it is new material and you have never encountered it before. Okay, so let us go one by. Which one do you want to do first, the chemical one or the bio one? Or both together, I don't care, but we have to do both. At least introduce the stuff today. Okay, let's start with the bio part. Now, I gave you the cell growth equation, right? It had standard notation. In other words, A, B, C, D, E were the stoichiometric coefficients, and then there were all the subscripts to define the number of atoms of hydrogen, nitrogen, etc. in each mole of substrate, biomass, etc. Right? Unfortunately, the book that we have uses a little different notation. So, but you can read it in chapter 7 there. But the notation that I have used is the standard Minkiewicz-Erickson notation, which is what we grew up with and we were taught. But the notation and the subscript that are used in Schuler and Kargi is different. So let us stick to one notation, which is what I started with for the assuming the biomass is the sole product, right? So now what I want you to do is to take the same framework that we had in the previous class, but also consider now the formation of an extracellular product. Okay. And this product is also accumulating during the growth phase. That's very important for us. Otherwise, we can't write the reaction balance and equation, right? And now we take the previous equation that you wrote and extend it to include product synthesis. Give different notation for the product, different from what we have given. And now write me the more general reaction balanced equation. Is my question okay? Follow exactly what we did last time, but now worry about a new stoichiometric coefficient, which is for product which is connected to the growth phase. Okay. See, this equation that I want you to write will only hold if product formation is directly linked with cell growth. Okay. Suppose I have a secondary metabolite like in penicillin fermentation. I can't write this equation. We don't want, that is all for Atul Narang and others to worry about in third year in bioprocess technology, engineering, etc. But here we are assuming, we are taking for granted that we have another extracellular product, and we are saying that this product is different from biomass, and we are saying this is also directly linked to growth. Okay, it's directly linked to growth, so that you can have a new equation and you can extend the previous equation to incorporate this product, which has its own stoichiometry. So write that equation, and then the next question I want you to figure out is, how do we find out? Because now when you have a known product, another product with its own stoichiometry, you'll have another coefficient. So how do we find out its stoichiometric coefficient? These are the two questions on the bio portion. Just see if you can work it out. And I will try to answer this after you attempted it. If you want, I can give you a parallel question on the chemical side, because now we have only time till early next week. We have to finish both of these things, so there are some loose ends. If you want, I mean, we can have a counterpart question for the chemical side also. 1 minute. Let's see if can you see the slide? Actually, we have.
No, sir.
Good. So you remember, that on the chemical thing, I discussed the equation that you are very, very familiar with, right?
Sir, we are
Essentially,
not able to. We are
no.
not able to see the slide, no, sir.
Okay. Okay. Anyway, I will see why it's not showing, because I asked share it, but 1 minute. But meanwhile, you please worry about the problem I gave you on the bio thing, right? I will give you a counterpart question on the chemical thing. I have asked it to show, because for chemical we are doing the by slides, no? So I asked it to show. Is it still not showing?
No, sir.
Now?
Nothing.
Okay, doesn't matter. Forget it. We can do it without it. I don't know why it's not, it's been working every time, but this today it doesn't seem to show. Nothing's lost. We what? So let us frame the counterpart. I mean, another question for the chemical side, right? So what I, please take it down. So what I said is, if I can say that I have either a constant pressure process, or I have a process where the Cp has negligible dependence on pressure, at least compared to the dependence of Cp on temperature. That is the specific heat at constant pressure. I can have a similar thing for specific heat at constant volume, but since most of our processes are indeed carried out at constant pressure, or if for low pressure systems I can neglect that dependence, I'm choosing Cp. And that's very nicely tabulated Cp as a function of temperature. So I can take that Cp as a function of temperature, integrate it with from T1 to T2, and that will give me a delta H, right? That is a very general, they are all state functions. So I will get a delta H, which is a sensible heat change. Now, normally Cp is represented as a function of temperature in number of tabulations. And what is tabulated is Cp in the so-called, with the Cp with the P as a subscript and Ig as the superscript, where Ig refers not to ideal gas but ideal gas state. That is, we are neglecting dependence of the real gas on pressure. So you understand, ideal gas state doesn't mean, because one thing we said is we are going to remove this approximation of ideal gas. Ideal gas state doesn't mean the gas is ideal. Okay, it means that the gas is absolutely real, doesn't follow ideal gas law, but we are only saying that the dependence of various parameters like Cp as a function of temperature is very strong compared to the very weak dependence on pressure. So that is an ideal gas state. Okay, there is negligible or no dependence on pressure. So normally what is tabulated is Cp by R, the gas constant, and that is given as alpha plus beta T plus gamma T squared plus delta T cubed.
Sir,
Yeah.
sir, I shared my screen with the PPT. So like with the
Is it
PPT,
working?
sir, I have to ask other people.
So is the screen, are you seeing it?
Yes, yes.
Okay.
Visible.
Doesn't matter, even if you don't see it, it's just a simple equation. Alpha, beta, gamma, okay, are all constants for a particular real gas. They will be given to you. I mean, for every system, it will be different. So that those are all tabulated. I mean, maybe we can find where those tabulations are. We'll do it. We have time next week for that. Sometimes the different people tabulate them differently. The NIST database doesn't tabulate it this way. It tabulates it as alpha prime plus beta t to the power minus 1 plus gamma t to the power minus 2 plus delta t to the power minus 3, for instance. Okay, it doesn't matter. All you have to do is just a polynomial. It's just an integration, and you will take that, you know, the value of the gas constant, you know, alpha beta or alpha prime beta prime gamma prime whatever, and you will just integrate it, and you will get integral Cp dt, and you can go from 298 Kelvin to whatever temperature the reaction is carried on for every species, right? If I have methane CH4 plus O2 plus going to whatever CO2 and H2O, I can do it for methane, I can do it for oxygen, I can do it for nitrogen, because I know alpha beta gamma or alpha prime beta prime gamma prime, and I know the functionality with temperature, and I'm assuming there's no dependence with pressure, and I can integrate it, and I have the sensible heat change delta H due to each component. Okay. Now, what I want you to think on, and this is a more interesting question. What I really want you to think on, and I don't know whether we can answer it today or tomorrow. What I want you to think on, just as like the product equation, product in the bio portion, how to extend the reaction to extracellular product formation, which is something that you can think on. Similarly here, suppose I don't want to do this integration. And suppose, see, I want to linearize this in some way. In other words, I want to linearize this in such a way that I just take a temperature difference above 298 Kelvin. Suppose I'm carrying the reaction at 400 Celsius. So 400 plus 298 Kelvin minus 298 Kelvin, because that is where the data is for. And I want to take that temperature difference and I want to multiply it by a certain value of the specific heat, such that I get the same result as given in the slide, which is obtained exactly by numerical or analytical integration. In that case, I don't need to each time take alpha, beta, gamma, or alpha prime, beta prime, gamma prime, or A, B, C, D, whatever are the values. And sometimes they are given to the fourth order. You know, there are corrections now till fourth order, not just linear, quadratic, cubic, but to fourth order. So I don't want to then do those corrections, but just basically take the temperature difference, and I have the entire delta H by integrating by just multiplying by the difference in temperature, and it should give me the same result as if I have integrated it, or negligible difference. So how do I linearize this? So that's something I want you to think on, because today there are tables available by which I can just do this with this short form, and I will share these tables with you before our before you go on mid-sem break. Okay, so your one question to think on the chemical part, another question to think on the product stoichiometry biological part, and we have to develop both these things today or tomorrow, and also do the available electron balance, and also worry about constructing a path by which the heat of reaction, which is only available at one temperature, to 25 degrees Celsius, we can extend and get Q equal to delta H for a steady state process at any temperature. That is requires at least one full class. Okay. So please think on these two questions and let us see if we can arrive at answers for them. So what is it that we have done? We've continued with our bio portion. We've done exactly what we have been doing till now, but now we are saying, let me extend that to an extracellular product formation. And since I linked it to directly to the growth process, the same type of equation that we wrote earlier is valid. But now I need to have an extra coefficient of stoichiometry for the product. Of course, this will introduce an extra unknown, and we have to see how to get that extra unknown from. That's a separate question. But first, let us get this generalized equation, and this goes one step beyond what we did with biomass as the sole product. So please write that stoichiometric equation and then see how you will evaluate. Then we have to see how to evaluate the coefficient. That is, on the biochemical side, I just ask you to integrate Cp dt is not a problem, because you have Cp as a function of temperature when all the constants are given to you for every compound, right? You can do that for each compound in the reaction. So now what I ask you is, if I have to linearize this such that I just multiply by the temperature difference, so the reaction is not taking place at 298 Kelvin, and yet I want more or less the same result as you would get if you were to integrate Cp dt with all these constants. So how do you think we should do this? इन दोनों पर आप सोचिए, and Let us discuss this after 10 minutes. Are my both questions clear? And why we are doing it? Okay, I will repeat it in a different language. Why we are doing the product stoichiometry business is that it is not always clear that biomass has to be the product. So we have to generalize our equation to include a product other than biomass. So that's why we are doing it. Okay. Because in biotransformations, why should only biomass be the product? Okay. In the chemical part, we have divided everything into two: heat of reaction, which we have not yet dealt with, and the sensible heat changes, which you already know how to deal with, which is an integral Cp dt. Cp is given as a function of temperature, and we have neglected pressure dependence. So you can actually integrate what is there in the databases, and you can get the delta H for the temperature from 298 to whatever temperature you're preheating the substrates or the reactants and whatever products, whatever reaction takes place at and whatever products are coming at the elevated temperature, let us say. Generally elevated temperature because it is a combustion type process we are studying. So you can integrate all of them. Now only our thing is we also have a heat of reaction, which we can't neglect, and when we have to find the net Q is a net delta H change, this includes both sensible heat change as well as heat of reaction. So but the reaction, if it were taking place at 298 Kelvin, it would be very simple. We would just add all the three. We would take all the reactants, we would integrate it with alpha plus beta plus T plus gamma T squared plus whatever delta T cubed or whatever the function is. We would do it for every reactant. Then to that we will add the heat of the reaction delta H naught reaction at 298 Kelvin. Then we will take the products and again we would integrate it and we would add all these three. Our problem comes if the reaction is not at 298 Kelvin. That's the problem we will come to maybe Monday, but probably on Wednesday. The immediate problem is, suppose I don't want to integrate it. You can integrate it, it's not a problem, but data has to be given. And suppose I could find an equivalent linearization, which would take me much less time. What would I do? What should I do? Okay, think on these two questions, and I will ask you and let us try to answer them at 12 o'clock. Okay. Now, if we have quorum, we have to answer this. We'll complete that part, right? Then we are left with available electron balance. I need one full class. We are left with how to do the path, how to create a path such that we can integrate the information even when the reaction is being carried out at a temperature other than 298 Kelvin. That's a class. And I think we should actually do some examples of actual calculation. So itna hame karna hai, and let us spend an hour today, and then we should be finished definitely. At least an hour we should do today and as extra, and then we will be finished with the course in time. Okay, is par sochi, and 12 o'clock I will discuss with you again. Okay. How are you all doing? So we had two questions. If we have to incorporate formation of an extracellular product, what does the overall balance equation look like? And secondly, if the base temperature in the chemical reaction system was taken as 25 degrees Celsius, and suppose we, instead of integrating Cp with all the numerical constants alpha, beta, gamma, delta, etc., if we have to have a linearized version such that there's negligible error between the linearized temperature difference T minus T naught, that is where T naught is the base temperature of 298 Kelvin, that multiplied by whatever it is that is some indicator of Cp or transformed Cp will give me exactly the same result as the integral. To solve the first question, why don't you go back to our old reaction without the product? That part remains unchanged, right? We don't need to rethink that situation. Because you remember we had all the stoichiometric coefficients with C as the coefficient for the biomass, etc. O reaction remains the same. So please write that and modify it. So the reaction will look as follows. So you had the CWHXOYNZ plus AO2 plus B times the nitrogen source formula that we already had, HgOH This gave us C moles of biomass with the formula CH alpha, O beta and delta. It gave D moles of CO2, E moles of H2O. And now we have to add H moles of an extracellular product, and we have to give different stoichiometric coefficients for that. So something like JKLM. So C times J times H times K, O times L, and N times M. So F is the stoichiometric coefficient for the product. F moles of CjHkOlNm. Okay, this is the notation we have followed throughout, different from the notation in the book that I gave you, which is in chapter 7. That's why I can't take the equation from that book and paste it. Okay, because the notations are not the same. So 1 mole of the substrate reacts with A moles of oxygen in the aerobic system. It uses B moles of nitrogen source, gives you C moles of biomass, D of CO2, E moles of H2O, and F moles of the extracellular product CJHKOLNM. Now we have introduced a new variable because small f is also not known to us. So there is an extra unknown stoichiometric coefficient in this equation, right? So now think where the additional relationship between the coefficients can be obtained. It is required, no? Where you are going to obtain that additional relationship from. I again repeat, this is only valid if the product is directly linked to growth. It cannot be applied to every metabolite production, okay? Or every fermentation. Actually, we were one equation short. Now we are two equations short. So where do we get the new equation to evaluate another new variable or coefficient of f that we have introduced into this extra unknown we have introduced now? So find a way to solve it. We must do on the same analogy as we did for the biomass. So what is that analogy? Did you all get the overall equation? With small f additional parameter? Okay. How did we get small c from last class? I showed you how to obtain the value of small c. How did we do it? Can anyone tell me? Okay, last time I showed you that the stoichiometric coefficient small c is related to the yield coefficient yx subscript y subscript xs. Okay. And basically, if I know the molecular weight of the dry cells and I know per unit molecular weight of the substrate, which I do, and so C times the dry cell molecular weight divided by the molecular weight of the substrate gives me Y subscript XS, the so-called biomass yield, which I can measure. And so I can get C from this equation because I know the dry cell and ash weight to which I will add, and that is the numerator, that multiplied by C divided by the substrate molecular weight gives me the experimentally measured biomass yield. And so the only unknown here is small c. So I can always have an equation relating small c because experimentally I have measured the biomass yield. Can we not do the same thing here for the product? Why not? Yes, we can. Okay, the numbers have again dwindled to single digit. 20 odd, it has come back to below 10. Okay, let's give you the answer to this. So basically we have to determine another yield coefficient experimentally. Otherwise we have no way of obtaining small f, and the appropriate coefficient is the product yield per unit substrate, what is called y subscript ps, which was one of the 10 yield coefficients that your book defined. So yps we can define y subscript ps as the grams of product form per gram substrate consumed. Grams of product form per gram substrate consumed. This is something that you can measure. So just as we looked at the biomass yield yxs, we can relate yps also to the stoichiometric coefficient small f because we know the molecular weight of the product, desired product, and we know the molecular weight of the substrate. So yps is small f times the molecular weight of the product divided by mw of the substrate. Molecular weight of the substrate. So f molecular weight of product divided by molecular weight of the substrate gives me the product yield from substrate y subscript ps. Okay. So once we have this experimentally measured yield coefficient, we can readily find the value of small f. So now we have a carbon balance, we have an H balance, we have the RQ value, we have two measured values coming from biomass yield and product yield based on substrate. So we have these 5 relationships, but you have now 6 unknowns A to F. So we are one equation short, and I suggested last time that for this we need to balance the number of available electrons from transfer of oxygen, from transfer to oxygen. And this I said, I hinted it is conserved during the entire metabolic process. So that is the important topic that we want to complete by tomorrow. And on the chemical part, I, in a way, gave you the answer. I hinted the answer. Basically, if I were to integrate from Cp as a function of temperature dt and integrate it from the base temperature T naught of 25 degrees to the operating temperature of capital T, I will get the exact heat change for delta H value. Now, if I could divide this by delta T, which is T minus T base or T minus T naught, which is T minus T of 298 Kelvin. And if I were to multiply it by some mean Cp, such that when I multiply that mean Cp by T minus T naught, I get exactly the integral value. That is called a mean way of a linearized mean Cp, and then it is very easy for me to calculate the heat change. In other words, the equation for this looks as follows. So we define a mean heat capacity, Cp mean heat, which when you multiply by, here it says T2 minus T1, I said T minus T naught, where T1 is 298 Kelvin, T2 is the operating temperature at which you are carrying out the reaction. So for every substance participating in the reaction, if I have a mean value, which I will give you a graph for that, I will share a graph with you on Wednesday. So that Cp mean into delta T is your heat change, sensible heat change. I can do that for every reaction. So I don't need to even integrate once I have that graph. But what does this mean? It means that this Cp mean H, you have to evaluate for different outlet temperatures, which I call capital T and which this slide says is T2. So in other words, suppose I go from 298 Kelvin to 500 Kelvin, I have a different Cp mean H. If I go to an outlet temperature of 1000 Kelvin, I'll get a different mean value. And similarly, if I keep changing the outlet temperature, I will tabulate a different higher Cp, so that when I multiply it by the delta T, I get the delta H change due to that substance or that species. Okay. So those are the answers to that. So now all we have to do is integrate on the bio side this reaction with the available electron balance, and that will be our course. And on the chemical side, we have to find a way to integrate, because see, this Cp mean, this you can do at any temperature, but the heat of reaction we have to include, but that's at 298. So we have to devise a suitable path. So that's what we will do in another one more class. So in summary, these are the two things that are left in our course. And once you do that, you can look at energy balance for any chemical reaction, however many reactions there may be. Okay, once we devise this path. So let us spend a class doing that, and let us spend a class doing the available electron balance. And you must remind me to share with you the Cp mean information for various gases, CO, CO2, NO, NO2, oxygen, nitrogen, methane, etc. Okay, I have it, but it's just that I may forget. Okay, so please revise all of this, and tomorrow and Wednesday, let us try to finish these two important things. I need one class for each, and then let us. I'll give you an example problem. You can solve it. Okay. In general, if it's single digits, I don't particularly. But anyway, I hope you have understood this. I will again. I will reinforce this business tomorrow, and I hope that you will be able to grasp it and actually calculate it for any reaction. Devpriya, is it okay?
Yes, sir.
This part is clear. Let us do it one more time tomorrow, and because we are now coming to the fag end of the course. Okay. And I hope you will do as well as in minor one, which I am really thinking of giving everybody almost full. I don't want to deduct for a few people. Okay, I will. But let us discuss these aspects because this involves little more calculation. So that is all I want to actually show you how to do this path business and how you can integrate and how you can combine it with the heats of reaction. That part is left. So we are down to very few people now. Anyway, I hope by tomorrow, when I reinforce this, others will also be able to grasp this. If there is any question, please ask me now itself, or so. Let's. If you have any query, I can answer you these questions. You know, I mean, we have time today. So if there are no questions, we have to do three things: available electron balance to get the remaining unknown in the bio equation, stoichiometric equation, and we have to devise a path for doing any chemical reaction. These two things we have to do. We need a class for each, and I have to share with you the CP mean information for all possible gases. Otherwise, you have to consult tables and get alpha, beta, gamma, delta, and that's a much larger table, and we can't do it in one. It's not in one place. Okay. Okay. All right. I guess that's at least if we repeat this concept tomorrow, I think, and then Wednesday, I think it should be all right. Maybe more people will. At least you guys will be able to understand it for sure. All right. Thank you.
Thank you, sir.